Thanks, Rick. Everybody can hear me, hopefully.
Yep.
Yep. The CEI grant came up, and obviously it had some reasonably tight time constraints. So within the exploration team, we talked about projects that we could possibly put forward, and the idea of assaying a bunch of soil samples that had been taken along the Mount Dore corridor that had only been analysed with portable XRF had come up. And so we put that together into a proposal and were successful. So the Mount Dore Corridor, it's right in the heart of sort of Chinova's exploration ground on EPM 10783. It's a long-standing EPM within the Eastern Succession. 26k long, like well endowed corridor with known copper gold, molybdenum and gold cobalt systems. And really the focus had been quite singular on copper and gold with cobalt as an aside at Mount Cobalt, but the potential for new economy minerals and even other economic commodities hadn't really been fleshed out entirely, we felt. And so the CEI grant really allowed us to explore that possibility, and it was a possibility that probably wasn't worth exploring without external funding from the Queensland government. So just a brief summary on the geology. So basically the Mount Dore Corridor is situated over the top of a major structural boundary between the Maramo-Staveley and the Kurradaala-Selwyn domains. It's a structural boundary sort of defined by a easterly dipping D2 with reactivations during D4 events in the Mount Isa orogeny, and it's been designated as the Mount Dore Fault. On the western side of the fault, there's the Staveley Formation, and then on the western side, there's the Kurradaala Group, and it's been assigned to the Hampton Slate unit within the Kurradaala Group. And a major feature, or something that really stands out obviously in the belt, is that there's two Williams supersweet granites that are intruded into the deformed metasediments, and they are the Mount Dore granite and the yellow waterhole granite. And then in places along the belt, the basement geology is draped by Mesozoic sediments that have been attributed to the Gilbert River Formation. And the star line is shown on here, and I've just shown star 222, but star really won't be discussed in this talk. So just to give a snapshot of some of the data that we had along the belt, we had nearly 20,000 soil samples along the belt, and nearly 15,000 of those were only ever analysed with a portable XRF. Some of them had already been sent for lab assay. So it was a matter of going through and selecting a subset of samples that met the budget constraints of the CEI grant, and still provided a reasonable amount of spatial resolution without losing too much east to west. So the original soil sampling parameters, they were all east-west lines. There was sample spacing down to 15 metres. So where we've taken every second sample, that spacing is still 30 metres for regional data sets, still quite tight. Line spacing was down to 40, and now the majority of them, after subsetting, it's at 60 to 120 metres, like north to south line spacing. All the samples were sieve samples at a -20 mesh, internal review for PXRF processes. Sort of said that we didn't lose that much in PXRF analysis by using a -20 mesh fraction, and it saved a lot of time in the field. And with nearly 15,000 samples being taken, saving time in the field was a major consideration. And I think another thing too, along the belt, copper and moly were the major commodities of interest, and portable XRF does a pretty reasonable job on picking up those sort of anomalies and trends fairly reliably. And yeah, all the XRF data, it was all done on workstation within controlled environment as much as it can be. So in total, yeah, 3,727 samples were subsetted and sent for assay to ALS in Mount Isa. And then they dispatched it all to ALS in Perth so that it could all be in one facility, all controlled, and also assayed within the time constraints, because some of the wider, or the, I don't know, far-sighted sort of targets for when assays might be returned were outside of the time constraints. So we really wanted to make sure we got them back in time, and it gave me enough time to actually look at some of the data. So we subbed in QA/QC samples at a ratio of 1:25, and just here on the top, just these are some of the sample methods, and all the top ones are fairly standard. But with the primary samples, we had to add in an additional pulverization method, because when we started looking at the samples, and particularly the sample weights, we always tried to aim for about 100 grams to 150 grams per sample in soils, but inevitably some are less than that and some are more than that. And we had some samples down to 60 grams, 70 grams. And so using fire assay methods, it really didn't give the option of re-assay should there be failures. And also there was a lot of discussion with lab and also some industry colleagues about the you know, whether or not using a -20 mesh sample would actually reliably assay, particularly on the fire assays, issues with the flux and those sorts of things. So it was just decided that we would pulverize all the soil samples, but they do represent a -20 mesh fraction if you're keeping count. Just going through the methods, these are all the ALS method codes. So we did multi-elements with 4-acid digest, with about ICP, MS, low detection limits. Rare earths were an add-on package to that 4-acid digest. Precious metals, we got our gold, palladium and platinum using lead fire assays with an ICP, MS finish. And then some of the resistive elements, like cerium and zircon, we had assayed using a lithium tetraborate fusion with an ICP-MS finish to actually pull those over range values out. And then over range gold was just a your normal 30-gram fire assay method. So for this talk, I kind of wanted to focus in on the new economy mineral elements that were the subject of the grant. Yeah, so to give you a little bit of like economic element context, some of the samples that are over 750 ppm copper or over 0.036 ppm gold highlighted in green and yellows. And then germanium was something that flagged early in other areas where I'd done soils at -80 using portable XRF and then assayed them using the same methods. Germanium was like a real, I don't know, I suppose fact checker for anomalies in the particular area I'm talking about. There was arsenic anomalies that would have had you continuing to chase anomalies, and sort of germanium showed that it wasn't vectoring in the way that arsenic was showing. So thresholded that at 0.42 ppm, that's sort of above background, and it's sort of highlighted here. And you can see germanium is also up there and above most of the rare earths. And I've just summed all the rare earth elements in together for the sake of display, just so you can see it. So that's great. These are all the little picks, the above background values. But the real crux of it was, out of these elements of the CEI grant, what were actually of interest at the end of it. We found with our platinum and palladium, there was a lot of quantization going on. So they weren't significant amount of samples in orders of magnitude above the detection limit of the method. And we really had to sort of discount. So it was more of like a relative sort of usefulness. So unfortunately, we didn't find the next bushveld in the area, and so we don't have a juicy PGE deposit to add to the copper gold mineralisation in the area, unfortunately. But yeah, the grant was also about moly and rhenium, and obviously we've got the Chinova has the Merlin deposit. They're the yeah, that's the resource for Merlin. So 1.5% moly, 26 ppm rhenium, 0.3% copper, yeah, 6.4 million tonnes. So a reasonable size, I suppose, new economy mineral deposit. So part of doing these soils as well was to look at in a more quantifiable way rather than PXRF is, well, can we actually detect these things at surface, and what does the surface sort of signature of, you know, a Merlin or Merlin-like system look like? And then you can see that in these, that with the green and the gold, that, you know, cobalt, silver and moly are sort of associated strongly with, you know, traditional mineralization as opposed to new economy mineralization. So on to rare earths. This is just a spider plot normalized to C1 chondrite. And you can see that a lot of the rare earth elements were enriched in light rare earth elements and depleted in heavy rare earth elements. That may be like what Ken was suggesting, a problem with the assay method, and potentially if we were seeing some more interesting heavy rare earth values in the area, we'd consider going back and doing some, you know, fusion methods to actually flesh these out. But something that really stood out for me was obviously the enrichment in light rare earth elements is quite strong, sort of suggests a bit of cryptic metasomatism. But it's really that dip in europium which made me start to think that, you know, the rare earth elements are actually associated with a fractionated source. So I'm saying granites. There's two massive granites right next to a lot of the mineralization. So kind of explored that a little bit with rare earth elements. And largely, yes, the rare earth elements were associated with granites, but not entirely. And this kind of took me by surprise in particular areas. So that's the light rare element oxide in weight percent, and heavy rare earth plus the yttrium in weight percent. And you can see actually the heavy rare earth elements are strongly partitioned inside the granites. That's a rough outline of the granite body. But the light rare earths actually stick around some of the major structures in the area. And then in both total rare earths, there's this particular halo in and around the Lady Ella deposit, and that's it's a pit in that sort of area, so there's no soils taken over that area. And when you look at the mapped geology in the area, and going out there myself and having a look, this blue area that's been pointed to by the question mark is actually a Mesozoic mesa. So I started wondering whether or not these rare earth elements are actually it's been influenced by the Mesozoic and its potential, because a lot of the Mesozoic sediments, particularly in Queensland, have been derived from explosive volcanism along the east coast when Australia started rifting and opening up the Tasman, and, you know, that pre-rift sort of sequence. So there's potential that some of that felsic volcanoclastic derived sediments that have been reworked have actually created some of this influence in the area, but that needs a lot of more ground checking. But in reality, the rare earth elements were at low level anomalies, like low, anomalism, but they are soils. So some of this needs to be taken in context of them being soils and not rock chips or fresh drill core and that sort of thing. In the east over here, there's a lot of mapped pegmatites, and there's potentially some hypotheses of the Mount Dore granite poking into this part of the world, and that's actually something that really needs to be followed up, because there's obviously potential for rare earth element hosted in pegmatites. But the main benefit I saw of the rare earths was that, in particular the light ones, is that they actually become like a really strong pathfinder element. And cerium in particular was strongly associated with a lot of the traditional mineralization that we'd seen. And cerium was one of those elements that was frequently over range and had to be zapped with fusion. So onto the granites. I mean, it's a major lithology along the Mount Dore Corridor, and the rare earths were obviously strongly associated with them, with the exceptions that I mentioned before. I think a lot of the rare earth elements were associated with the accessory phases within the granites: monazite, xenotime, titanite, allanite, and zircon, obviously. And that's really shown up in the zircons. There's a really strongly linear trend between hafnium and zircon that really says that, you know, zircon and hafnium and a lot of the rare earth elements that have a strong correlation with zircon and hafnium are all coming from the granite. And that ties back in with that europium, that negative europium anomaly. It's that the rare earths are really coming from this fractionated granitic source. And then, yeah, there's two populations in the data, and they really probably should be treated separately. But these are the over-range zircon values. So we're starting to get zircon values in excess of 2000 ppm, which is quite something exceptional. But I'm not sure that we've got an economic zircon deposit anywhere, particularly in granites, when you can go and mine a beach and get plenty of zircon. So, I mean, that's a positive thing. We don't have to mine granite for zircon, but yeah, it's half knowing where not to look and what not to look for and not what to do as well. So that was a win. So started looking at a lot of the other elements, a lot of the Pathfinder elements, to see how they sort of sat along the belt. It's been so well mapped, we're able to actually do this in a semi-informative sort of way. So we found that tellurium, bismuth, beryllium, selenium, antimony, and thulium really sort of tracked hydrothermal activity. And they were really strongest in the northern block. So I'm sort of focusing on that Lady Ella sort of area. And you can really see that, you know, selenium and tellurium in particular really map out that Mount Dore fault quite strongly. There are some exceptions, and antimony over here, there's maybe a bit of zonation to the hydrothermal activity that's occurred along the fault. And I'm not sure if it's getting stronger, but Mount Elliott is just to the north here, so maybe it is, and that's suggesting a bit of a halo. But again, this area east of Lady Ella is quite interesting in its Pathfinder elements. And we have done a small amount of drilling in this sort of neck of the woods, but I think, you know, what this data is saying is that we should start looking a bit further south of there and considering some other options. And then in the southern area, it's the same sort of story, but different elements are doing different things. So if you look at beryllium up at Lady Ella, really strong, mapping some sort of hydrothermal activity. And then when we go down to Victoria, which is the southern end, it drops away and it's just not anomalous at all. But bismuth is really strong in the major structure of the Mount Dore fault, as is tellurium. Selenium is a little bit weaker, and thulium is sort of only in this neck of the woods and down here, and there's some mafic bodies. And when you follow this line up northwards, you start heading into the Mount Cobalt, New Hope sort of deposits, which are those cobalt, gold, and a bit of tungsten sort of systems that Ken has done some work on for the GSQ and for us on. And maybe it's saying that we need to treat this part of the world a little bit different. And then again, this whole southern part of the world needs to probably be treated to the northern block of data. So one of the advantages of obviously getting, 53 or 54 elements and having a really almost complete digest, and then actually getting the complete digest with the fusion, is that you can start doing some litho-geochemistry with your soils. And these are just some plots that I've just basically taken after Haley in his paper this year that was in SEG, and you can see start having some real compositional groupings and trends, and it really reflecting, you know, sort of metasediments, mafic intrusions, felsic intrusions, and then mafic felsic, you know, dominant metasediments in the area. And then as the rare earth content increases, like, you know, the confidence in the data interpretation increases. And what I mean by that is when you've got the high rare earths and you see some of these other trends, you can really start to pinpoint and say that, yes, I think that the rare earths are actually you know, in the granites and associated with hydrothermal systems that are associated with granites, whether blind or not, in an IOCG setting. And then, you know, with that litho-geochem, yeah, the soils have basically gone across this whole corridor. And so you really are able to actually start pulling out all of these separate units into different beasts geochemically. And that's like a major advantage of this data set that we didn't have previously. We can actually start to create a bit of a geochemical fingerprint and start thinking about economic element, Pathfinder element, and even just compositional sort of indexes for each of these bodies. And that's something that I'm slowly working on with the data ongoing. It's a bit of tedium though, but sort of getting there. And then there was actually a few outliers in the data. Gold was found to be anomalous, more than 10 times crustal abundance using the 95 Madonna and Sun values. But gold also wasn't always with tellurium, which was surprising, particularly down in the Victoria part of the world. You can see tellurium is really strong over the top of the Mount Dore fault, albeit patchy, and gold, yeah, above crustal abundance just really isn't associated with it. So we've got to understand why that is in this particular area. And then also, I got really excited when I started getting the assays back, and I never got a gold result, and there was an overrange gold assay pending. I was like, oh my goodness, this is crazy, it's a soil. And it came back at 21.6 grams per ton. I'm like, that's it, I'm taking the shovel out there and I'm gonna start panning. And it turned out to be the sample that was immediately adjacent to the Victoria waste rock dump. So I wasn't best pleased, and that's not a photo of the nugget that I found at the soil sample site, unfortunately. So yes, caveat emptor on some of your assay data, but interesting nonetheless. So some of the other work that needs to continue on from these assays is obviously the litho-geochem and the indexing that I was talking about, but there's also a whole suite of drilling that's happened along this belt. We've got Lady Yellow, an old mine. We've got the Mount Dore deposit, Merlin. There's a lot of drilling. Not all of it's diamond, and I would say 85% of that is with an aqua regia digest, and some of it is really only assaying for economic elements. But I need to start looking at the drilling data and projecting some of these surface anomalies at depth where I can to actually test it out. Also, now that I have you know, nearly 4,000 data points for assays versus XRF, we can start to work out a way potentially how to normalize some of our XRF data and just see what's happening with that. And along with the geochem, start to look at some of the publicly available, I might add, hyperspectral data sets along the belt. So HiMap is one particular suite of data along the belt, and start to pull apart potentially what geochemistry is lithology based and what is alteration based, and potentially what that means for vectoring towards similar styles of mineralization elsewhere in our tenement package. And the benefit of this data set and the HiMap data set being publicly available is other explorers can take this sort of data from a well-endowed belt and hopefully apply that and make discoveries elsewhere in the eastern succession. I was talking about indexing, and I wanted to have a look and see if there was already any sort of existing economic indexing that had occurred. And the Geological Survey of South Australia had actually put together an IOCG index based on fresh core samples from drilling in the eastern Gawler Craton. And I thought, well, I know it's the eastern Gawler, but we'll see how it applies. And they kind of suggested that values above 0.8 on the index were of economic interest. We maxed out at 0.67, but again, it's soil samples, not a fresh drill core sample, but it does reflect a lot of the trends and areas of interest that have popped up just by looking at the raw assay results. So it's a first pass, and we probably should try and come up with our own IOCG index for maybe the eastern succession, maybe just the Mount Dore corridor, but it's a first pass approach, and it's actually an index that anybody can use using the IOGAS software, and they can go and have a stab and see what sort of trends sort of come out of it. And something, you know, that's really important, obviously, not all IOCGs are the same. And I think it was Richard Lilly that suggested that not all curries in the clone curry are the same curry. And then even if you know what kind of curry you have, let's say example, Tim curry, you never know which kind of Tim curry you're going to get. And that's something that we really see with the northern and southern blocks of this data. So it's, yeah, again, you've got to take context into consideration when looking at these results. So just some of my final thoughts. You know, a 4-acid almost complete digest with a low detection, nice EPMS finish. I see it as a must if you're going to be doing this type of work. The fraction size is important, not import. Apologies. So minus 20 mesh wasn't ideal. Had we had more material and potentially not lost as much, I probably would have got it sieved down at the lab to a 75 micron fraction. So the soil data, you know, you lose a lot of that geological context that you get with core and rock chips, obviously, but it's still informative for your regional litho-geochem. Rare earths, they can provide some really meaningful additional information, and some new economy mineral deposit types have been ruled out in the belt, such as PGEs, and we could also see that existing new economy mineral deposits in the corridor, you know, can be detected by soils, and they can be detected with PXRF, but more quantifiably when you have an assay. And then potential along this belt from this data is that we've possibly got some other new economy minerals that we hadn't yet given full consideration. And I'm really talking about the light rare earth elements. I've really got to go target some of these pegmatites, have a look at them, maybe get some petrology on them to see what sort of mineral species we've got. But a major one, and it was the focus of the grant as well, is silver. We're finding that silver is actually really anomalous along the belt, and somewhere like the Mount Dore deposit, maybe go look at the resource itself and see what kind of silver credits potentially can be added to it. So I think immediately from this CEI grant, there's potentially some real economic benefit that has come out of it almost immediately. And you can really see that there is variability along the same structure. It's 26 Ks strike length. There's multiple deposits and commodities, and they've all got different pathfinders. And every IOCG terrain is unique, and that uniqueness is even down to the local level. And just a few acknowledgements, obviously the GSQ for supporting it, all previous and current Chinova exploration team members, field techs who collected 20,000 samples along the belt. Thank you very much. My industry colleagues for discussions and bouncing ideas, and a special mention to Senior Geo from Chinova, Ian Faulkner. He originally designed the program and supervised it, and was the main reason that I could have a pretty high degree of certainty in the PXRF data, because of the amount of work that he put into just nutting out those processes and making sure it was all tickety-boo. And there's a few of my references. So thank you.